This section covers 2.1.2 for POE. Uh, Here they have it listed as introduction to structural member properties. The activity says it is beam deflection. We're really looking at beam deflections and how beams are deformed and what causes it or what slows it or what stops it. The moment of inertia, this nice long definition, what's important to know is it tells us important information about how a cross-sectional area is distributed about the centroid. Keep in mind that the centroid is the center of gravity or the center of mass of an object. What we really need to remember, because we're going to look at something else slightly different, is that we're looking at the stiffness of an object related to its shape or related to its orientation, related to how it's set up. Something also that's nice to know is that a higher moment of inertia has a greater resistance to deformation, or it's stiffer. The higher the moment of inertia, the stiffer it is. Here we have two boards, one turned one way and the other just rotated around. We have a joist and a plank. If we look down here, beam A, the top one is the joist. That's what you see in the floors of your house. It is 1.5 inches wide and then 5.5 inches high. It has down here, as you see, an area of 8.25 square inches. The plank, which is what you see on your deck patios, is going to be 5.5 inches wide and then 1.5 inches high. Both orientations are very good for different situations and for very different reasons. They're asking what distinguishes one from the other. It's mainly just the orientation, just how it's set up. And if we look at this, we see which one, under the same amount of force, which one deflects or has a greater amount of deformation than the other, which one is deformed. And it's going to be plank B. To find out why it did, we look at the moments of inertia due to the orientation of the beam, or due to how it's set up, how it's laying there. In the case of the joist, we have the base across the bottom, and the height is from left to right. Here's the height, here's the base. So this was 1.5 inches wide and then 5.5 inches high. To find the moment of inertia, I use this formula. What's really important to remember is that we're dealing at everything is in inches, base and the height, and that the only item in this that's raised to the third power is the height. The greatest mistake I see is that people try to do base times height and then raise it to the third power. You take your height to the third power, then you multiply it by your base. So looking at beam A, or the joist setup, you see here we have 5.5 raised to the third power, which is 166.375. We multiply that by the base of 1.5 inches, divide it by 12, and we get 21 inches to the fourth power. The inch to the fourth power is what we measure the moment of inertia in. So that's something to keep in mind. If you see inch to the fourth power, you're looking at the moment of inertia, or how stiff something is due to due to its shape or how it's oriented. Looking at the plank version, beam B, our base is 5.5 inches. So we multiply that by the cube of 1.5 inches. Notice we cubed 1.5 inches. We did not cube 5.5 inches here. Multiply all of it out, and I got 1.5 inches to the fourth power. So here we have, it's showing you the two different moments of inertia, so you can see both of them. For beam A, it's 21 inch to the fourth power. For beam B, it's 1.5 inch to the fourth power. So the joist orientation is 14 times stiffer. So let's look at a few shapes, or a couple of shapes here, and say why they pick one over the other. Let's assume both of these are going to be steel. So we have this entire item here made out of steel, and we have this entire item, the I-beam here on our right, made out of steel. If we look at the area of both of them, you can see that there's a greater surface area for the block on the left and a much smaller surface area for the block on the right. But if we look at our moments of inertia, you can see that the block on the right has a much higher number for the amount of surface area. This is why you see I-beams in construction, why you see I-beams in all the skyscrapers. For a much less amount of material, they're able to make something almost as strong. Not to mention it requires less reinforcements because it weighs significantly less. So to look at the modulus of elasticity, we talked about the stiffness of an object related to its orientation or its shape. Now we're going to talk about the stiffness of an object related to its material chemical properties, or what it's made out of. We're really looking at with the modulus of elasticity, it's a ratio of some specified form of stress to some specified form of strain. That'll pop up again later in statics. So in general, a higher modulus of elasticity produces a much greater resistance to deformation, or it's able to withstand more being deformed and return to its original shape. So let's look at two different items here. The A is going to be the Douglas fir. This is going to be made out of wood. It's going to be made out of plastic. Let's look and see which one is stiffer than the other due to what it's made out of. Because if we look down here, all of our dimensions and everything else is exactly the same. The orientation, our moment of inertia for these is exactly the same. So that's not the portion we need to be concerned about. Okay, so the only difference between the two here is that one is plastic and the other is wood. You see the plastic deforms quite a bit more here. It goes down much further, and it does come back to where it was. So the difference between the two is the modulus of elasticity. It's the ability to deform and return to its original shape. That's what's important here. I can deform something, and if it doesn't go back to its original shape, then I've damaged it. It's no longer good anymore. Also keep in mind as we're going through this, we're looking at elastic. If you look at the elastic waistband of a pair of shorts that you may wear, a pair of basketball shorts, they're supposed to stretch out and then go back to where they were. So deflection we measure is delta max, or how much it's moved. We're going to look at the applied force, or the load that's applied to it or put onto the item. The length of the span between the supports, that's what's important to remember. It doesn't matter how long it is, it's about what the span is between what's supporting it. The modulus of elasticity, which we'll introduce now, as well as the moment of inertia, which we've already talked about. So to find the beam deflection, or how far it's going to move, I have a formula. It's my force times my length to the third power. Only the length is being raised to the third power. That's being divided by the number 48 times my modulus of elasticity and my I, or my moment of inertia. So if I look at the two different materials, our moments of inertia were exactly the same. However, our modulus of elasticity is something very different. This is either a number you can look up for common construction materials, and you can find it anywhere online, or you are given this number, or it's a number you try to solve for by plugging in different numbers into this formula. And the force is going to be the same for both of them at 250 pounds. So let's look at the beam deflection for A. I plug everything in. Notice I use 96 inches here, and I'm raising that to the third power because the length of the board is 8 feet. 8 feet converted to inches is 96 inches. 8 times 12 is 96. I divide that by all these numbers multiplied together, which was 48 times my modulus of elasticity times my moment of inertia. My final answer is that this will move 0.12 inches under 250 pounds. So if I put a load of 250 pounds on here, the most it'll move and go back to its original shape is 0.12 inches. If we look at beam B, once again I'm using that 96 inches, that the 8 feet converted to inches. I'm using my modulus of elasticity of 419,000 psi, or pounds per square inch. I multiply all of it through, and I get that this will move over ½ inch and return to its original size. So if we compare the two, there's 4.2 times less deflection in beam A than there was in beam B. Something to keep in mind about beam deflection, just keep an eye out for what you're measuring, how you're measuring it, and then just use simple normal algebra that you've been using since your freshman year.